spires, steeples, and domes. They are all intended to make us look up. In the case of the church, heaven is what we're supposed to see. But in the secular world, there might be a different inspiration.
In antiquity, one could make the argument that nature is sacred. I think we have to imagine the entire cosmos. We have to imagine nature as being a place that's full of gods and mythical creatures and deities of different kinds.
Well, we can go really far back into antiquity to take a look at sacred spaces. The suggestion is that Stonehenge is a sacred space. And we're not certain, but the thinking is that that was a place of worship. What were they worshiping? Something in the sky. Was it the sun? Was it the moon? Was it the stars? Was it all of them? But what we see with that is a concerted effort to create something man-made that will connect with something heavenly.
As we move into the classical era, which, by the way, typically refers to 5th century BCE to 3rd century Common Era, Greek architecture is characterized by a post and beam system with columns holding up the weight. You can see Doric and Ionic style columns in the Acropolis. Later, the taller, more ornate Corinthian style. Here's a fun fact. The Roman Colosseum includes all 3 ancient architectural orders.
As Christianity starts to transform Rome from a religious perspective, it also starts to transform Rome in terms of its temples.
Christians could take just about any existing building and transform it into a Christian church.
What we see with the advent of Christianity, particularly in the 4th century, with Emperor Constantine, the first officially Christian emperor, is that public spaces are transformed into public Christian spaces. The most significant of those is the Basilica.
And the Basilica was a Roman building. It was quite simply a public hall.
It's rectangular. It is divided typically into 3 aisles, a central nave, a row of columns on either side of that, and then 2 aisles. And it is a long passageway up to the emperor's law throne. Then it becomes a long walk up to the altar when the basilicas are transformed into churches.
That eventually became connected to the development of what's called Romanesque architecture, which was barrel vaults, vaulted ceilings with rounded arches, as a consequence of these rounded arches, you had to have pretty massive side walls to support the roof structure.
So that is a key component of structural design, is trying to figure out how to support the roof. And obviously one of the big challenges is if you want a big open space, you have to have a big open roof area, and so supporting that becomes very difficult. One way to do that is with an arch, because an arch curves and it pushes the force straight down against the other pieces of the arch, which eventually come to rest on the wall supporting the side of the structure.
The soaring arches that we think of in the Renaissance churches is not happening in the 500s, 600s, 700s. They're brick, they're heavy, sometimes they're stone, but there's not an awful lot of light.
You could say that's a metaphor for this time period, which is sometimes referred to as the Dark Ages. But if you think about it, there were all kinds of innovations taking place.
I think it was an inherent understanding of the physics rather than written mathematical principles. So it came from experience. These were master builders, master stonemasons that really understood how to create these structures that stood the test of time. So the mathematics and the physics are expressed in the structures themselves.
So while they might not have written it all down or tested theories using the scientific method, They did rely on the same principles of physics we understand and utilize today.
So statics is the science of making sure all the forces balance to zero. So Newton articulated that force is equal to mass times acceleration, and we really don't want buildings to accelerate. So you want all of the forces to add up to zero. So when you take a look at a building, it's very important to resolve the forces. And we think of forces as engineers as being applied in 3 different directions. The forces would be either vertical forces, front to back forces along the length of the auditorium, or side to side forces across the width of the auditorium.
And even in the so-called Dark Ages, there is a quest for light and height.
This changes when we get into Gothic architecture. It's a kind of architecture that rejects the rounded arch as the basic building principle.
It's a pointed arch that marked Gothic.
In the Middle Ages, there was an attempt to get larger open spaces in the cathedrals. So this was done by increasing the height of the arches. As the height of the arches increased, the lateral forces, the thrust forces that they create became higher. So flying buttresses were added external to the arches to help resist those lateral forces that were coming from the taller arches.
You can see the flying buttresses walking around a Gothic cathedral.
It's an enormous innovation because what it does in terms of weight bearing is free up the walls. You can have more window, right? Which is not going to necessarily be weight bearing, but rather allowing light into the church. The ability to have a church that is flooded with light makes that church into sacred space that reflects the Christian belief that Jesus Christ is the light.
That's the really amazing thing to me, is that their mathematical tools for this were very limited. So it was mostly done by trial and error and experience, and they did it kind of by experiment almost. They'd build scale models and play around with different things, but they didn't have the kind of an advanced mathematical understanding that we do today.
And that brings us to today. We understand a lot more about statics, what keeps a building standing, and also about the external dynamic forces that work against it.
I designed sensors and sensor systems to monitor civil infrastructure. There are lots of reasons we would want to monitor civil infrastructure. The main reason is to maintain the safety of the structure and maintain the functionality of the structure. We want to measure any changes in the response or the behavior of the structure that may indicate that there's damage. And if we can detect that early on, then we can provide repairs or maintenance to that structure before those changes become potentially catastrophic. Structures are typically designed with a certain design life, say 50 years, 100 years. And often structures last long beyond their original intended design life.
Take bridges, for example. According to the American Society of Civil Engineers, more than 2 million trips are taken every day across bridges that are structurally deficient.
So as a result of age and just normal everyday wear and tear, structures can undergo some degradation. We can see corrosion develop in steel elements. We can see cracking in concrete or spalling in concrete. So these are things that can happen just due to the age of the structure and normal environmental conditions. The forces that act on structures can be thought of in 2 main categories. One is the everyday wear and tear, the everyday loads that act on a structure. So on a bridge, that might just be the traffic that goes over it on a daily basis. Then we can also consider more extreme loading events. This would be things like extreme storms like hurricanes or perhaps earthquakes. And so the types of damage that can result can either be from deterioration over time, or it can be more extreme damage due to kind of unexpected or unusual loading events. We have a shake table where we can induce a base excitation like an earthquake to a model building. This allows us to test different control strategies for the building. It also allows us to test some of our sensing capabilities for earthquake and wind loading on structures. Also, I was going to say on the bridge, we have some wireless smart sensors that have the computer and the radio built in, and so that they communicate data with each other and also back to our base station for detecting the damage in the structure. In general, sensors measure a physical response in the structure, and then our job as engineers is to take those physical responses and correlate them to potential damage in the structure. So those physical responses may be measuring the vibration of the structure, measuring the motion of the structure, or they may be measuring specific things like corrosion in steel or metallic elements, or they may measure the actual strain that the material is experiencing. Smart sensors take it one step further. Smart sensors provide microprocessing capability at the location of the sensor so that we can process that data and actually learn something about how that response correlates to damage in the structure. This is the wireless smart sensor that we use in our research for structural monitoring. It has the ability to measure structural vibration, so it has a 3-axis accelerometer, the kind of accelerometer you might actually have in your cell phone. It also has the ability to measure temperature and humidity, and we can even measure light. So what's going on this top board are all of the sensors. The brains of the wireless smart sensor and the radio are here. So we've got a microprocessor which allows us to process the data on the sensor itself. And then we also have a radio for wirelessly transmitting the data and the processed information. These types of capabilities are beneficial because they not only improve the safety of the structure, but they can lower maintenance costs and extend the life of structures. This makes structures in general more sustainable.
While they didn't use the word, early builders did think about sustainability. Many sacred spaces from the medieval and Renaissance periods are still standing. And there is another similarity to what we see today.
The same kind of interesting race going on for the highest buildings. They tend to be office buildings or combination office buildings, perhaps living space type buildings, but it's a little bit reminiscent of what was going on with Gothic architecture in the 12th and 13th centuries.
That's where the human aspect comes in. Competition between cities, between communities, between monastic orders to have the biggest, brightest, tallest, shiniest church.
And today, maybe there's a different kind of competition taking place in modern sacred spaces.
The stadium is a kind of sacred space for the ritual Saturday afternoon ceremony, as it were.
There are those who worship money, right? So those huge bank towers that are steel and glass with their floor-to-ceiling windows, the IMP buildings, you see them in Chicago, you see them in Toronto, banks, right? So is that the new sacrality? And the Freedom Tower, even the naming speaks to what it represents. But it is about Renaissance. It is about building on the ruins of the past, but at the same time immortalizing the events that took place on that sacred space. And I think that's precisely the point with the Freedom Tower, is to send a signal that rebuilding is possible, and height will mark progress. And we will move forward.
There are sacred spaces everywhere, perhaps in places we would not expect.
Which may be the inspiration for looking up and ahead to a time where technology and imagination can create the spaces of the future.